In this module, we will look at converters for DC and AC motor drives, and we will also look at semiconductors that are used in these converters. So let's start with a converter for DC motor drive, and as you can see, we need two switching power poles as shown here, pole A and pole B, and they are controlled by these two switching signals QA and QB. And you can see that the output of these power poles here are defined as A and B over here. And let's hypothetically think of a point N over here. So this is really a hypothetical point, lowercase n, but whereas the DC bus negative side is defined by capital N over here. Okay. So if we are asked to, and we are given an input voltage VD here, and let's say we are asked to produce some average output voltage V0 over here. So that's what we want to do. So what we'll do is we'll make the voltage of A with respect to this hypothetical neutral, this voltage to be half the desired voltage, and we will make the voltage at this point B with respect to this hypothetical neutral here as minus of that desired output voltage. And you can see that the voltage between A and B then would be equal to the desired value V0 over here. So we know that we cannot make the output of a pole voltage to be negative. So what we have to do is to introduce a common mode voltage in both of these poles. So that's what we will do. We will, so what we'll say is that by introducing a common mode voltage here between this point N and this negative DC bus N over here, we can then make this voltage of A with respect to N to be equal to this voltage plus this common mode voltage here. Similarly, we can make the voltage at this point with respect to the negative DC bus, this one over here, to be this which we calculated earlier or decided upon earlier, plus this common mode voltage. So what should this common mode voltage be? Well, you can take any value, in fact, but I think the most logical would be half the DC bus voltage. So you can make this V0 go the same amount positive as you can make it go negative. So that's the reason why we'll pick this common mode voltage to be half the DC bus voltage. And that is what is shown in this figure B here, that you have a common mode voltage. And then, you are creating this VAN to be V0 over 2, and here minus V0 over 2 here. And then that ends up being the desired V0 over here. So by substituting this common mode voltage in this expression here, the voltage of pole A with respect to this negative DC bus is given by this expression, and the output at pole B is given by this expression over here. And if you subtract these two, then the output voltage is really dA minus dB. Well, first let me define what dA and dB are. dA, which is the duty ratio of this switch here, would be given by this. You just take this and divide it by both sides by VD, and you'll get this. You take this and divide this by the input DC bus voltage VD, and we get the duty ratio for this switch. And you can see that this the output voltage V0 that we want to synthesize in the first place is dA minus dB multiplied by this DC bus voltage. So you can see that in this converter, this V0 average could be anywhere between minus VD to plus VD over here, right? All right. So Let's move on to three-phase. Quite often they are called inverters, but you can call them converters for AC motor drives. So once again, you have a DC bus voltage here, and you would like to synthesize some low frequency AC, usually sinusoidal, across this AC motor over here. An AC motor can be represented by some inductance, and at the back there's a back EMF, so to speak. So you'll see that if we can replace these switching power poles on an average by these three ideal transformers with controllable duty ratios, and the duty ratios are the turns ratios, and these are given by 1 to dA, 1 to dB, and 1 to d sub c over here, right? So following what we have seen in case of the converter for DC motor drives, what is going on is that we once again introduce a common mode voltage in all these three poles. So we have this common mode voltage shown over here, and then on top of that, we have what we are trying to synthesize between A and this neutral of this machine, which is VAN. Similarly, what's between here and this, there's this, and between this and this, what we are trying to synthesize this. Okay, so those are listed over here, and with this common mode voltage, and once again, one of the choices is to use V common mode to be equal to Vd over 2. Okay, and this is called sine PWM. So if you're using sine PWM, this is what we will pick, and you can see that the voltage, average voltage of point A with respect to N would be given by this, and similarly for B and C over here. And if you divide these expressions by Vd to get the duty ratios of these switches, and therefore the turns ratios of this transformer representation, dA would be this, dB would be this, and dC would be this here. Okay, so in this you can see that this VAN average, or you can talk about VBN, take any of these poles. This cannot be less than 0, and this cannot be greater than VD over here. So that would, and if you're using a common mode voltage of VD over 2, right, then the peak value that you can have for any of these phases, its maximum value of this peak is VD over 2. Okay, and that way, it didn't come through here very well, but the line to line, forget about this here. The line to line voltage maximum would be, it will turn out to be square root of 3 times this value, which is Vd over 2 here, right? So, which is given by this expression here. But there's another way to do this, well, let me erase this here. Let me erase this here. Resolving. So what this symbol here is nothing but approximate sign over here. Okay, so the maximum value of the peak line-to-line voltage in this sine PWM, this turns out to be about 0.867 times the DC voltage coming in here, VD. Okay, but there's another technique called space vector PWM, which we'll not go into in this course, but it is possible to make this to be equal to VD. So we can get higher output voltage out of these converters if you use this so-called space vector PWM as compared to what I just described here was a sine PWM. Okay. So let's come to these devices that make up these converters. They are available in very large voltage ratings. The current ratings are in kiloamperes. They can switch very fast, and the on-state drop is also very small compared to their voltage ratings. and this cost is going down here. So what are these devices? Well, one of them is MOSFET. So if you're using it in a converter where the maximum voltage that these guys would see is 200 volts or less, then I think MOSFET is a pretty good choice. And the symbol for this MOSFET is shown here. And we can draw it like this, recognizing that there's a switch here which turns it on or off, but there's a parasitic diode in anti-parallel, and the drain current versus drain to source voltage for different gate to source voltages, they are plotted over here. So the advantage of MOSFET is that you have an insulated gate, so you need very low current. Basically, you need some charge to turn it on or off. You have to recognize that there's a built-in diode, as shown here, in anti-parallel over here, and the on-state resistance when this MOSFET is fully on, and that is given by this slope of this characteristic over here, it depends exponentially on the voltage rating. So that's why I made the statement that if we are using this below 200 volts, then it's a fairly reasonable choice, because beyond that, this on-state resistance may be quite high. And so that justifies this statement. And certainly these can turn on or off very fast compared to any other device. So if you have high switching frequencies, then this also makes it a good choice. But the workhorse of motor drives really is this so-called IGBT, insulated gate bipolar transistor. So here's the collector, emitter, and gate over here. So it's really, you can think of it as a combination of a MOSFET and a transistor. So it has the benefits of both. You have an insulated gate, like in a MOSFET, so you have a fairly low drive requirements. And then like a transistor, bipolar junction transistor, BJT, you have fairly small voltage drop between the collector and the emitter when it's conducting. And therefore, unlike a MOSFET, which somewhat are limited to lower voltage ratings, you can use these in very high voltage ratings, and up to 3.3 kV are probably now much higher than this. These devices are available, and current ratings in hundreds of amperes, and you can parallel them to get whatever you want. So the characteristic of this device, the collector current here, I sub C, and the collector to emitter voltage for various values of gate to emitter voltages are shown here, not unlike those in MOSFETs here. And also now we have smart power modules where not only we have the power devices, but the gate driver ICs are even included in them. So that makes it very easy to use to make up a converter. So that brings us to the end of this module, where we looked at converters for DC and AC motor drives, and we talked a little bit about semiconductors as well.